Our first speaker is Philip Webster, who I do not really know. Come on up, Philip, as you make your way up here. I'm going to say he's with KT Groundwater, which is Mike Keister's company. And we are super happy to have him here. A lot of modeling experience. And until I read this bio, I did not know a fellow Tarleton grad, bleed purple. And so welcome Philip to the stage, and we will listen to him talk about the investigation of aquifer compaction potential in Montgomery County. Thanks, Philip.
So hello, my name is Philip Webster. I am a hydrogeologist at KT Groundwater. This afternoon, I'll be presenting on the potential for aquifer compaction within Montgomery County. The aquifer compaction potential was assessed using a lab analysis from cores extracted from the formations within the Gulf Coast aquifer system. This was an exciting study, as the analysis conducted on the cores is the first time since the 1970s within the Chico and Evangeline aquifer, in the first of the kind for the deeper Perkinville and Jasper formations. Also wanted to shout out to my co-authors of this study, Mike Keister with KT Groundwater, and James Beach and Chris Drebeck with Advanced Groundwater Solutions. All right, so before we dive in, I wanted to acknowledge the entities, the labs, and the people that made this study possible. Lone Star Groundwater Conservation District, whose regulatory area is Montgomery County, funded the project. And props to Lone Star GCD for recognizing the importance of collecting and analyzing this kind of data, which will benefit the policymakers and the scientists of the greater Houston area in understanding compaction. Also wanted to thank the Porter Special Utilities District, who provided the site where the drilling and the core extraction occurred. And due to the complexity of the lab analysis done, we had multiple labs that were utilized. Okay, so here is a quick outline of the discussion. So first, we're going to just briefly talk about the compaction and subsidence and why it is occurring in the area. Then we'll review the Porter site and where the drilling occurred and the data that was collected. Then we'll dive into some of the results. Notably the clay mineralogy and the compaction properties from the consolidation test of the course. And lastly, we'll review how we use this data and future studies. Okay, so a little review on compaction. First, I just want to go over the difference between subsidence and compaction. So subsidence is the change in land elevation at the surface, typically in response to subsurface support. So this is the cumulative effect of subsurface processes such as fault movement, plate tectonics, formation, compaction, while compaction is the thinning of a geologic interval. So our focus is typically on compaction that occurs due to groundwater withdrawal, which causes a decrease in water level and therefore an increase in the effective stress. Sorry, is there a laser on here? Okay, well, I'll just point you on the right direction. So the equation for effective stress is given at the top there. So this is simply the geostatic stress subtracted by the effective stress. And so the geostatic stress is the stress occurring in the downward direction caused by all the geologic material, the fluids, and the urban loading, while the hydrostatic pressure is the upward pressure of fluid in the pore space. And of course, so the difference between these two is going to equate to the effective stress. So for example, if our water levels are decreasing, our pore pressure will decrease, and therefore our effective stress will increase, resulting in compaction. So finally, let's turn to the figure on the right. So within the Gulf Coast aquifer system, we have inner beds made up of mostly clay. These inner beds are fully saturated with water. And so as we pump water from the coarse grain material, the blue area in the figure, or the aquifer, we create a pressure difference between the fine grain inner beds and the aquifer, resulting in water seeping out of the inner beds into the aquifer. This movement of water from the inner beds results in a decrease in pore pressure, and again, therefore, an increase in effective stress, and therefore compaction. Okay, so here is a quick map of the Porter site where the cores were collected. The Porter site was in southeastern Montgomery County. Also, I included 4 sites that I'll refer to as the Gavrish and Bonnet sites, which actually collected cores throughout the Chico and the Upper Evangeline from the 1970s. And on the right, we have a stratigraphic column of the geology and hydrogeologic units at the Porter site and Gavrish sites. When we get to the analysis section, I'll focus mostly on using the terminology in the hydrogeologic unit section. I just wanted to point out too, before we move on, that at the Porter site, we did collect core from the top of the Chico, or to the Chico from the bottom of the lower Jasper. So here's just a quick picture of the site. It's nothing fancy or too pretty, but I just wanted to include something in there. But on the final report, we'll have some more pretty pictures there for you. Okay, so here are all the core that were collected at the site. So in total, there were 18 cores collected from the Chico through the bottom of the lower Jasper. So we had 3 from the Chico and 3 from the Burkeville, and then 5 from the Evangeline, and 4 each from the upper and lower Jasper. So to the right, we have the resistivity and the gamma ray logs of the borehole, with the depth at which each of the core were collected, which is shown as the gray horizontal lines. Now you can see we had a pretty fair distribution within each of the aquifer units for the core collected. Okay, so here is a list of the analysis conducted on the core and the geophysical logs run at the site. The bold are mentioned in this report, or at least included in this report. I don't talk too much about the permeability test, but they are included into the results that we'll get to towards the end. But yeah, just to reiterate, there was quite a bit of data collected as far as these core data, so we just wanted to focus on these few things, but when the report does come out, we'll of course have covered all of this. Okay, so let's dive into the clay mineralogy. I want to first go over the different types of clay minerals. So clays are a combination of tetrahedral and octahedral layers with different bonding agents, where the bonds between the layers affect the amount of water that can seep in and therefore the expandability of those clays. We will go over kaolinite, smectite or montmorillonite, illite, and chlorite. Some results are given, so that the smectite, some of the results were given in terms of smectite and some were in terms of montmorillonite. For the purpose of this study, we will use those terms interchangeably. And then I'll get to the mixed layer group when we're done reviewing the 4 main groups. So looking at the diagram to the right, we have our 4 main groups. The kaolinite, the octahedral, and the tetrahedral layers are bonded directly with one another. If we move to the illite, they are bonded with available potassium, and the chlorite is bonded with the brucite-like compound. If we look at the smectite, on the other hand, is bonded with available cations like sodium and calcium. And these bonds are weak enough to allow water to be incorporated into the bonding between the layers. So of the major clays, smectite or montmorillonite have the most expandability, while the others have very little expandability. So this is important due to if a formation is not very smectite or montmorillonite dominant, then we wouldn't expect too much compaction to occur. So let's go back to the mixed layer group. Clay minerals can transform from one to another, given certain environmental conditions. The one we'll focus on is the transformation from smectite to illite. So with enough temperature and availability of potassium, smectite will transform into illite. And this was an interesting question we had, and we found it to be pretty important just because smectite is expandable and illite is not expandable. So the lab conducted X-ray diffraction on all of the cores. X-ray diffraction is an analytical approach to quantify the clay minerals based on their unique crystal structures. This allows X-ray diffraction to distinguish between clay minerals, such as the smectite or illite, any mixed layer groups, and other non-clay mineral species by analyzing their characteristic diffraction patterns. And then we also applied a method using the spectral gamma log to estimate the clay minerals, which will be compared to the X-ray diffraction results. The spectral gamma log separates out the radiation into thorium, potassium, and uranium. Using these different ratios of the radioactive elements, we can then estimate the concentration of each of the clay minerals within each of the intervals of the log. Okay, so here are the X-ray diffraction results. They were averaged per hydrogeologic unit. So as you can see, it's pretty overwhelming that they were all pretty dominant in the mixed layer illite smectite group, with only minor or trace amounts of the chlorite, kaolinite, and the illite mica glauconite group. There was a higher concentration of smectite than illite within that mixed layer group. Another thing to note was that there was no discrete smectite, but that may have been because there was a low concentration, and therefore that got included into that mixed layer group. But overall, between the different aquifer units, we didn't see too much of a significant change. Overall, they were all pretty smectite dominant. Okay, so now we can look at the results with respect to depth. So each point on this chart is a core sample. A few core samples were not included due to a high quartz content, and we didn't want to skew the results when we were reviewing them. So on here, the purple line all the way to the right is that total concentration of the mixed layer illite smectite group, and the red and green lines are those two minerals separated out. So overall, we did not see any kind of continuous trend with depth. Only a few trends within certain intervals. For example, if you look at, oh sorry, I forgot to add my labels to my aquifers here, but at the top there you have your Chico, and on the second top one is your Evangeline. So we did see a bit of a trend going from that Chico to the Evangeline. And I just also wanted to kind of go back to the smectite to the illite transformation. So if we were seeing more of that smectite converting into the illite, we would most likely see a higher concentration in these deeper intervals. And due to the temperature requirements of this transformation and due to the results that we see, if there is any transformation, it's at the very beginning of the stages where not much has been done. Okay, so now we can look at the spectral gamma results. So we use that thorium, potassium, and uranium concentrations from the spectral log to estimate the clay minerals. Before we review the concentrations, we need to first delineate each of the clay intervals that we'll use. So on the right, we have a spectral gamma log with our hydro units. We then converted that spectral log into the gamma index and then a volume of shale index, which is shown on the right, all the way to the right. The volume of shale ranges from 0, which would be no clay, to to 1, which would be 100% clay. Since the results are kind of a binary determination of either clay or not clay, we went ahead and assumed anything greater than 0.25 to be considered a clay. So if you look at the vertical line on the plot all the way on the right, everything to the right of there is going to be a clay, and everything to the left is going to be a sand. And we look at that, we can kind of look at the sand-dominated intervals as the upper Chico, you can see the upper Evangeline, the upper Jasper, and then for our clay-dominant areas, we can definitely see intervals within the Evangeline and Burkeville, and then the lower Jasper. Okay, so now we can take each of these clay intervals and plot them on a scatter plot of potassium versus thorium. So each area on this plot is designated as a different mineral that's shown in the bottom right in the legend. So something to note is that this method does not return the same X-ray diffraction, same clay minerals that the X-ray diffraction results would give us. But overall, we do see a pretty wide distribution of the clay minerals with this method. So we're going to look at a histogram real quick. Okay, so here are the histograms per hydrogeologic unit. So the overall distribution was similar across all the units. Like we saw with the X-ray diffraction results, we were pretty heavily dominated by the Montgomery or the smectite, and the illite. This approach does not consider non-clay minerals or any kind of mixed layers, and so it may not be quantitatively comparable to the X-ray diffraction, but the takeaway from looking at this is that this method did indicate that we were Montgomery or smectite dominant, which is the same as the X-ray diffraction results. Okay. When I showed the map, we also had the Gabbard and Bonnet sites, and they had a couple samples of clay mineralogy, so we wanted to also compare the Porter site results to those. Again, we should, not compare these results quantitatively because the results at each of these sites are going to be compared a little bit differently. The laboratory procedures, the technology, and our understanding of clay mineralogy has significantly changed in the past 50 years. But these are the most recent data that we have to compare to. But also, if you look at these, they were pretty heavily Montgomery dominant. And just a couple things to note was on the first 3 sites here, I could not find any documentation on how the samples were prepared or analyzed. And if you look at the Johnson Space Station, which is the last row on there, we actually were able to find some documentation, but as you can see, the mixed layer clay mineral was actually at 0%. So the reliability of these, again, is probably not as strong as the more current lab analysis. Okay, so now we're going to move on to reviewing the one-dimensional consolidation test. So a consolidation curve was developed for each of our core samples. On the right is the apparatus from the Texas A&M lab that was used. So essentially, the consolidation test increases the load on the sample within each cell. The sample compresses, and then the pore water is squeezed out. Once the sample reaches an equilibrium with the vertical displacement, the void ratio is measured, and it becomes another plot on the chart that you see on there, on the screen. So this is repeated by increasing the pressure, and there are a couple of phases where that pressure was actually decreased to show a rebound phase. So the consolidation tests were very useful in that the consolidation curve was able to estimate our fine-grained porosity, our inelastic and elastic specific storage, and our vertical hydraulic conductivity. As we discuss the compaction properties, we'll go into more details on these consolidation curves and how each of these compaction properties were determined. So one of our goals was to develop a depth-dependent relationship with each of these compaction properties. This will allow us to apply the compaction properties to other areas where the hydrogeologic units are maybe at different depths. So before we jump onto the compaction properties, we need to first find a way to convert that effective stress that we get from the lab to an effective depth. So we'll use the effective stress equation that we referenced before, which is shown on the right, or shown in the middle. So for the geostatic stress, we'll use the bulk density log that we got at the site, which is shown on the right. And for the hydrostatic stress, we will use a method developed by Eaton that uses that bulk density and a resistivity log to estimate pore pressure. With both of these, we determine the in situ effective stress at each of the core sites. The effective stress gradient for each core can then be used with each load step during the consolidation test to determine that effective depth. Okay, so since we get the results in terms of void ratios, we can simply convert that to porosity, and then the data that were greater than the in situ effective stress of that core can be analyzed, and that is what you'll see on the figure on the right. And we'll see that the grayed out points are from that Gabbard and Bonnet sites, and the squares with the different colors are from the Porter site. And so overall, we actually see very similar trends between all these sites. And also, just as a reminder, the Gabbard data is just looking at the Chico and kind of the upper portion of the Evangeline. But even across the different hydrogeologic units at the Porter site, we saw a common trend. Okay, so before we move on to the elastic and inelastic specific storage, I want to review how the compression and recompression indices are determined from the consolidation curves. So the compression and recompression indices are simply the change in void ratio over a change in effective stress. So these are important variables as they will inform these specific storage values. So on the chart, we have a loading phase, and which is where the effective stress is increasing during the test, and an unloading phase where the effective stress is decreasing. And you can see actually two phases where we're unloading on the chart there. Okay, and then I'm going to introduce another term, which is the pre-consolidation stress, and that is the maximum historical effective stress that formation has seen. And so once that pre-consolidation stress is met, the structure of the clay minerals is permanently changed. And so on here we have the recompression index, which is going to represent the change in void ratio over effective stress if the effective stress is less than that pre-consolidation stress, and the opposite for the compression index, which is going to represent that change in void ratio over effective stress after it has met the pre-consolidation stress. Okay, so let's go over specific storage real quick. And so we'll have the inelastic specific storage, and then we'll have elastic. This inelastic specific storage describes how the amount of volume released or absorbed due to a change in effective stress, and the inelastic condition, or the when the effective stress is greater than the pre-consolidation stress. And so similar to the porosity, we actually saw a pretty similar trend to the Gabbers and Bonnet sites. And actually about after 1,000 feet, the trends are pretty much on top of each other. So really consistent. Okay, and now we have the elastic specific storage. And this is determined using that recompression index, that reloading portion of the consolidation curve. And this is what will apply when the effective stress has not met the pre-consolidation stress. So if we look at the trends, we do actually see a little bit of a difference. And this may have been due to the Gabbers and Bonnet sites did not have any rebound phases in their consolidation test. So in previous studies, the elastic specific storage had been assumed to be about 0.01 of the inelastic. So the Porter data indicate that ratio may be a little bit higher. Okay, so lastly, we have the vertical hydraulic conductivity, which is the ease at which water can move vertically through the clays. So like we discussed at the beginning, pumping is from the coarse-grained material, or the aquifer, which causes water to move from the inner beds to the aquifer. And so as you can see on the trends on the right, we have the blue line and the black line, and you can see the Porter trend is about 1 magnitude less than the Gabbers and Bonnet site. And so what does this mean for compaction? So really, the lower the vertical hydraulic conductivity, the longer it's going to take for that compaction to be realized due to a disequilibrium between the fine grain, between the inner beds and the coarse grain material. And we do have another term that I didn't include on here, but I just wanted to make a note of, is we can't estimate how long it takes for that equilibrium between the fine grain and coarse grain to be realized. And in general, if we're 1 magnitude lower, then we're going to take 1 magnitude longer to actually see that compaction. So if before it took 100 years with the 1 magnitude lower in the vertical hydraulic conductivity, it's going to now take 1,000 years. Okay, so what have we done with this data so far? We updated and recalibrated the regional model that GMA14 uses for joint planning. This was done by updating the compaction properties that we just reviewed. Essentially, we used the best fit line through the Porter and the Gabbers sites to initialize the model, and then we allowed those parameters to be adjusted during calibration. This model is currently under public review with the Texas Water Development Board. The model files and the report can be found on their website. Since we did see some interesting differences between the Porter and the Gabbard and Bonnet sites, the biggest being that vertical hydraulic conductivity difference, additional sites would be really useful in the future, especially because this data has not been collected in the last 50 years, and I don't think we would want to wait another 50 years for this type of data to collect this type of data again. Also, I included on here a local model that allows us to more rely on that Porter data and allow us to refine the layering, especially looking at the upper and lower Jasper. And this would just allow us to develop a more reliable compaction model for Montgomery County. Okay, that is it. Happy to answer any questions.